get this.
Ei se niin haittaa, että toi ei näy. Sitten vielä varmistetaan, kato meidän yksi puhuja, koska mun mielestä hänellä ei ollut tietokonetta mukana, niin kun saan ton Aran tuolta.
Do you have adapter?
I do. I think I don't have it. I'm not sure. I have to, wait a minute. I think you can just ask somebody for one. Somebody will have one here. Or else we can just put copper wires and stick them in the hole. I do that.
Oh, really?
Oh, yeah, it works. I shorted out a whole hotel once that way, but...
Which mic do you prefer to speak? This is table mic or headset?
This is, yeah, I better use that, I guess.
Yeah.
Yeah. I don't get that plugged in. Maybe Fraser.
Joo, se on tollain jenkkiversio. Ei kun tossa oli toisella asiakkaalta löytyy. Näyttäis olevan. Yeah, where does I need to go? Let me see. So,
This thing doesn't always, it's working, okay, it doesn't work.
So Fraser's got this way, so we... Does it charge now? Yeah, it's charging. Yeah.
Thank you, sir.
It's charging, so it works.
Perfect, thank
you. And then Mike.
Yeah, Mike.
Turn other way. Yeah, thank you.
Is it good?
A little bit more. Oh,
My hearing aids are in the way? I don't think okay.
I have to adjust a little bit.
Okay.
No, it's perfect.
That seems good, yeah.
Yeah. And I turn it on. It might be on if I turn it now, so
Okay.
just let you know.
Okay, thanks.
Mirroring.
I got to enter the.
I think we need.
Oh, yeah. Did I not?
If you move it to the.
What? I have to do my password.
Now. And
Okay.
then.
That's not the one I want though.
Okay.
Yeah, let me make sure it's the right one. Oh, it's all set though.
I think we need to. It's
Okay,
mirroring.
I can do it.
Yeah,
I
yeah.
think. Oh, you're mirroring. Okay. I'm not so good at that.
Duplicating is. I think it's more.
What is it doing now? I can't see the.
Oh, yeah.
Yeah. So maybe if I push that, is there mirroring anywhere there? Is that it? Right there? Let's see. That looks. This is the. Where's my lecture here? Okay.
Take a look. Which one?
Which one? It's
This
back up for. It says right the one below that. The one you just back up Helsinki.
This one.
Yeah.
And then we just
Go to number one. Yeah.
go to
Slide one.
yeah.
Yeah.
And then
Right.
yeah. So now it. Thank you.
Thank you, sir.
Thank you. Thank you.
You're not even sweating.
Hei kaikki. Joo. Okay, we're going. If you see an empty seat right next to you, raise your hand so we know that. Because it's so good to see this lecture hall full. So good afternoon, all the friends and colleagues. It's my great pleasure to open this seminar. I'm Pekka Joensuu. I'm currently the president of Finnish Chemical Society. The role of Finnish Chemical Society is to advance the recognition of chemistry in our society overall. And this year is really special for us. As we have already mentioned several times, I tried to put also the webpage there, but Barry stole my screen. That's fine. That's perfect. Anyways, during this year we have a lot of events. And one thing that we wanted to make clear right at the beginning, I started pretty much similar way previously today. We wanted to target a lot of this program to young kids. I'm not talking undergraduate students. I'm actually talking about kids in the kindergarten and primary schools. Because you have probably seen last week in the media that chemistry is a little bit in a crisis. We cannot get enough students there. So Finnish Chemical Society want to put their effort and do the best they can also to improve the situation. On the webpage that was supposed to be there, it's Kemia100.fi. You can find these events. And I wanted to mention the kids first, but obviously we have also a lot of events for our society members and also to broader audience. So plenty of happenings. Please go there and see. And why we are here today then? It was the first meeting when we started to plan this anniversary, 100-year anniversary, that we decided we're going to have a proper scientific seminar here. And standing here today, I'm so happy that we really made it. Thanks to our fantastic speakers today, we're going to have a tour, a real magical tour, the world of chemistry. What we're going to hear today, I don't know. I really don't know. Actually, as Barry sent me an email, I don't know what I'm talking, or was it even your wife? I don't know what I'm talking. I'm going to talk something that is interesting. But I somehow believe that we're going to hear something about maybe chirality, maybe not. Hearing you say today something. We might hear molecular machines. We might hear something about maybe the central dogma of molecular biology. Who knows? But I'm not going to stand here longer to predict what we're going to hear. Instead, I'm going to give the stage to our speakers. And I would only like to warmly welcome you all here today and use this opportunity to thank at this point already our speakers, because I would probably have a chance to do it later. Thank you very much that you came here. We are really honored and blessed to have you here. Now, the first chair, Timo Repo, please.
So, good afternoon, ladies and gentlemen. It's really great to see so many of you here. My great pleasure and honor is to introduce Barry Sharpless to you. So he graduated in 1968 in Stanford. Then he stayed there for 1 year for the postdoc period and moved to Harvard for 1 year. And then he got a professor call to MIT, and then he was there for until from 1970 to 1977. Then returning back to the Stanford for 3 years. This is, by the way, a very important period in his chemistry work. And then actually returning back to the MIT the 1980 to 1990, and then returning back to the California, the Scripps Institute, La Jolla, and staying there the rest of the years so far. During the years, Sharpless and his team has been working on very interesting catalytic reactions, including catalytic oxidation processes, first general method for stereocyclic epoxidation of allylic alcohols, and then dihydroxylation, aminohydroxylation reactions for olefins. From this work, he has received numerous awards and recognitions, and particular one, 2001 Nobel Prize in Chemistry. And it was given for his work on chirally catalyzed oxidation reactions. It's interesting to notice that the original publication of this titanium catalyst are from 1980. This was the time when he was in Harvard and just moving to MIT, as far as in the scene. And these reactions are carrying his name. So Sharpless epoxidation, Sharpless oxidations, those you can easily find. And they are highly important for making pharmaceuticals and fine chemicals, and elementary part of modern textbooks of organic and organometallic chemistry. More recently, has been working on a very exciting concept, which is called click chemistry. This concept is very unique and nice and very fundamental in chemistry. It's just they try to take two molecular entities and put them together, quantitatively and irreversibly. And this is very exciting. And it has been nowadays used widely in polymer chemistry, chemical biology, material synthesis, and supramolecular chemistry. And this is actually what a really good chemistry is all about, identifying and inventing the reactivities. Sharpless has received a Priestley Medal Award of 2019, which is the highest honor in American chemistry for the recognition of his work. And this is a kind of straight question: invention of catalytic asymmetric oxidation methods, the concept of click chemistry, and development of the kappa-catalyzed version of A-side acetylene cycloaddition reactions. finally, what I think is also remarkable is that 25 or so group members from his group are research professors around the world. This is really an astonishing number in academia. Professor Sharpless, we are very much looking forward to your talk, and I guess it's part of visionary title about the chemistry for next 100 years. This is yeah, and I hope you in the audience will welcome him to the stage. Thanks.
Thank you so much for making me feel so warmly welcome here, and for your wonderful introduction and Pekka's inspirational, very modest way of describing how he got us here, and why Finland. Of course, it's a wonderful place. It's known as the happiest place in the world, or something. And you know, that takes something. My mother was from. My grandmother and grandfather were Göteborg and Kristiansand, not off the latitude line here probably. And so I feel very good about Scandinavian areas, and I just it just feels so cool around. I've only been outside a little bit. I had to write some other thing for at the last minute. So tomorrow, next day, I hope to see some of your wonderful places. Okay, I want to thank also my friend and longtime friend Fraser Schneider for enabling me to be plugged in here today and clicking the right budget gadgets. Okay, now click chemistry started. It may sound. In fact, my hope for the future is that chemistry just gets more and more efficient. I'm sure Fraser and everybody and Ada, everybody who depends on chemistry really wants it to be more efficient and more reliable. So it doesn't have to be click chemistry forever. This is just sort of a way to change the current, and I hope it just becomes chemistry goes back to being pure chemistry. But right now I hijacked a little bit the direction because I thought I could help chemists and others, and especially Fraser came in early because material scientists know they need to make connections. They're not fussy about them often. They need to have a connection, and so does a biologist, and so does surface science. Everybody who needs to have a bond that's stable knows what I'm talking about here, and they also know that we usually have to get down on our knees and pray for the reactions to work, right? I mean, that's just the facts of life, and we love our reactions, but what? Oh, yeah. Okay. Now, it was said by George Hammond, who's a great nonlinear thinker. He's a real character. He was at Caltech, and he for years went to Exxon. But we're not. It's not really correct to say that we're trying to make compounds. We really need functions and properties of the compounds. I think that's true in anything humans experience. That we're conscious and alive is because compounds are doing all kinds of dances and interchanging with each other. And this is a review by my friend and close collaborator over the years. He's an independent professor, M.G. Finn, and this was published, I forget when, but 13, okay. But in the end, I love the sentence here, to a unique extent among the sciences, therefore, chemistry requires synthesis. That's a pretty powerful statement, you know, because that's where we have our problem, right? Making and breaking the bonds that we want to make. And that's what life manages for us unconsciously all the time, making the right energy levels and making the connections by the electronic nerve networks. And so if we go and look at the priorities of synthesis, the first is reactivity. If you don't have a potential reactivity between two groups, then you can't have a bond there. If it's just back and forth completely in equilibrium, you're kind of in trouble too. So you need the reactivity that makes it go to a new compound. You get the connection. The connection is the real message, because like in life, once you connect to things like amino acids, that's the message, right? And then you put another amino acid. The message is the medium. The medium is the message. There's not any kind of tinkering and hammering around on the side chains of the amino acids. Life has got this figured out in the properties and functions. And this is a woman from Eastern School who was working for Craig Hawker. Craig is another one I owe a huge debt to, because we met thanks to a Rita and John and Rita Cornforth meeting in Sydney about 2000. It was really early, 2003, and he got started on materials with click chemistry, and he was very well known and a wonderful guy who travels the world. So this catalyzed the rapid acceptance of the copper reaction in material science. Oh, yeah. That's not the least of it. Here's one that is really, I like, because it's too many things showing at once. But all it is T-butanol and water here, the solvent, mainly water, T-butanol, copper wire with nothing but oxide on the surface. You know how it'll have the oxides. Cuprous oxide is what makes copper black. And so we're on the surface. So it can make copper 1. And so you put in a diazide in this case. This was done back in 2002. And phenylacetylene, 2 moles of that for 2 of these. And you start stirring it. And after 8 hours, it starts to make a catalyst, I guess. And this is the ligand. These things are ligands for the catalyst. So it makes its own world. And after 8 hours, and then after 24, it's virtually complete. And if you look in the solution, you can find about 10 or 20 parts per million of copper 1. And it's stabilized by the ligand. So you don't, if you have a copper, like in copper pipe, you can sweat it together with polyazide, polyacetylene. You don't need to heat it and maybe burn your house down when you're trying to fix copper water pipes in your house. And Valery Folkin did that. Okay, but here comes the punchline, because this reaction is faster. If you heat it, it's over in seconds. But if I do it in, if we just take a nurse and ask her to get some plasma from blood, and you centrifuge it, you can find that this reaction works just as well, if not faster, in fresh human plasma. Now that's the kind of thing that really changes. That's what you call strong inference. Strong inference by Platt, an article in '64, and Doug Fudge has written one in Science. Strong inference is, what do you do with information that makes you move faster than as fast as possible? And that is, you get multiple working hypotheses, and you say, if this is true, then you keep all these up at once, and you honestly try to kill all of them. Not your favorite one could be among them, but you honestly try to kill them. And if you think about it, you go to the worst case scenarios right away. Once you see a reaction that doesn't want to quit and you can't even stop, then you try something like this, and that saves you a lot of time. Saves you lots of time. Maybe years. And then it becomes a universal plug. This is a virus particle, and MG student had 60 azides, Chenois, the first bioconjugation work, and all 60 reacted, as far as we could tell, completely by fluorescent spectroscopy with dyes. That was weird. And then proteins and just about anything. It's a universal connector. But you can't use it around life too well, because copper is the catalyst, and copper is critical in our bodies for redox. And copper is a very slippery metal. Iron stays put and needs carriers, but copper is virtually down to femtomolar levels. It's regulated by femtomolar inside the cell by glutathione, which makes a tetramer, or is it a hexamer? This is shown by Christoph Farney recently, and so the copper is really slippery, but it's controlled, and it's needed to be where it needs to be. So it's interesting that copper is the catalyst here. Okay, so we had this reaction. This is a little bit strong terms, but think of it as a magic forge which hammers triazole links. Click. Anytime, any place, anywhere. And the hyperbole aside, is the only reaction I have ever worked closely with that has held out so well on its best secrets, more like an alien creature than a reaction. The biggest secret, of course, is how can any reaction be unstoppable? But perhaps for the moment, it's enough to know that there is one, and you'll recognize it when the going gets rough. It'll be the last reaction standing. So that's why if you're on a cliff and you need a piton connection to the rock, if you had a way to get the copper reaction involved, you might survive. Okay, this is Professor Sua Li, a wonderful Chinese student who is now a professor in Sun Yat-sen University. Here he is out in the West somewhere. And he had the guts to make thionyl tetrafluoride, which is a gas. And it's not like SO2F2, which is a baby compared to this one. This one, he risked his life to make it. Now we got a Chinese company making it. And Jia Jiadong has a kilo, and I have a kilo of this. And it's got an awful lot of potential to be really good for material science and biology, I think. I just wanted to show it with, I'm not sure, told this particular story, I don't think, with Fraser around, so maybe he'll find this interesting. This is what's so great about it. It reacts with amines like, this is an antimalarial amine. That's called dabsone as the NH2NH2. It was coming out of the war, after the end of the war, it came up in a screen, had some use. But here, it reacts with the two fluorines and just goes click right onto it and makes a nice crystal and stable to room temperature and water conditions. And then we do the click reaction, which is the suffix, and this is a really magical reaction. The rates here are enormous. It's like the QAC reaction. When it's going in its best form, in its best manifold, it's almost unbelievably fast. And what it does here is in room temperature, it makes we stirred it for 3.5 hours. It makes a singularity, this polymer. We've had those before from Vicane, but they were sulfates. So this is a polymer which has 600 of these links, sulfur links that it's made. And it didn't cross-link even. It's got an extra fluoride there. It could have made a hell of a mess, right? It's got a cross-linking capability, but it didn't do that. Its total dispersity is 1.6, and its molecular weight is 205 kilodaltons. That's how we estimate. And this is the product that comes out. The silicon here, this T-butyl silyl group, takes the fluoride away. That's why it's a sulfur-fluoride exchange. Fluoride goes to silicon, oxygen, phenol goes to sulfur. And next is the point that just want to make sure that's right. Yeah. This is the NMR spectrum. If you've ever seen the NMR spectrum of polycarbonate, that's what's used in bulletproof glass. It's in our, that's why it's safe to just go in labs with polycarbonate glasses. They're bulletproof. Really amazing stuff. In the NMR, well, I'm not sure the glass is bulletproof, but it'd be like more like that movie, The Godfather, right? With okay, so I've got the idea is that, in fact, this polymer is even more like polycarbonate because the polysulfate and this whatever you want to call it, imido-oxysulfate is basically in solution. It looks like a solution NMR, right? Very sharp lines. This is a proton NMR, and I think it's in deutero-DMF or deutero-DMSO or deuteroacetonitrile. Anyway, there's the carbon spectrum. You can count all 27 carbons if you want. And there's the fluorine spectrum. That's a standard. And that's the 600 megahertz proton. I don't know what that is, but it's a strong NMR machine, and it just gives a single peak. Now, what's that mean? If you're a stereochemist or organic chemist or just a chemist who's interested in how bonds display themselves in space, you realize that this is an asymmetric center. This dab zone piece and this bisphenol A piece, which is just like polycarbonate, but polysulfate too. This guy here, this side is different from that side. So this will be either R or S. Now, if it's R or S, how can it be? In other words, I have to say it right away. It's easier to say it. It has to be all R and all S in a given chain. Otherwise, it wouldn't have a singularity for a spectrum. I think it may be cyclic and it may be double helical. It's definitely helical. We're collaborating with Hans Sulhoff in the Netherlands, and we're getting some really great structural evidence from these polymers. We've made about 100 of them. You can put anything here and anything here that you want, and you can make really long spacers or short ones. But the only way I can understand this, and I'll say it quickly because I want to not take too much time, and that is the reaction that makes this bond is reversible, and it probably comes apart hundreds of times during the process of the polymer growing itself. The polymer, like Krischeldorf in Hamburg, Germany, the expert on polycarbonates and condensation polymers, Krischeldorf teaches that he thinks most of those polymers are cyclic, and that they're to the extent that they're reversible, they're heading for a place. It's going to be thermodynamic destination. They want to go to the lowest energy polymer form, and that's going to include the enthalpy and the entropy. And the entropy is very important in these polycarbonate type, in getting their structure to be monodispersed. Here, we don't have any reason. Well, even there, the reason for monodispersity is really mind-boggling. It's hard to see why they're so pretty good monodispersed. But this one's really monodispersed, and it's working on itself, is what I'm trying to say. It's either R or S, and it has if they were R and S, the thing is going to zigzag all over the place, and that's for sure when you look at the structures just by molecular models. I don't know if I'm making sense. Okay, here we come to the place where I'll just show it again. So we got this polymer, and it crashes out after 3 hours, and we stop and we filter it off, and 99% polydispersity is pretty good for. We don't have to. We can change the stoichiometry here, and the polydispersity doesn't change that much. I don't know what it thinks it's doing, but it has a way to know how to make itself. And here's the math. I know people in this part of the world are good at math, so here it's simple math. You just take 619 molecular weight per times 330. This gives the molecular weight of the thing, and then you get. Now you have to take the yield. To get the yield, you have to put the yield that this is right. It might be elevated by weight of solvent, but here it is. You put it in brackets, 99% yield to the 660th power, because that's how many links you have, is going to equal the yield. And so in order to get the yield to come out to 99, you have to have 660 times in a series. You have to have this level of yield to get to here. See what I'm trying to say? This is not a normal reaction. It's very much near perfect, just like the HUAC reaction. HUAC reaction goes 700 to 800 times in a row. In DCA, in PCR by Thomas Carell in Germany, and he gets all the things trisold without any light lesions, he says, and I can believe it. Okay, so both of these processes, Suffix and QAC, they're really running straight out. When they run straight out in polymer mode, they can remain pegged at 99%, even over 100 steps, or as you saw, even more than 100 steps. And here's the decay, first order decay. It's plotted a log plot, so you can see if your yield is 99%, and you're doing 100 steps, and we've seen this in other reactions where now we look at the yields for 99 steps just for fun, and we find, hey, 99% yield, if you're making 100 steps in a polymer like a ESF reaction, it's not good enough. You have a real mess at the end of the day. So that's a really demanding level of yield. Now, we went further because I just couldn't believe the singularity of this spectrum in the NMR. So we did another suffix reaction. Now remember, the suffix conditions are going to make all the suffixable bonds probably going. They're going to be, and you take the catalyst away, they lock up solid like a rock. They need the catalyst. But when the catalyst is there, so we're having another suffix step. We're going to take out this fluorine to make T-butyl fluoride, and we'll put in the phenol. And now we have the same problem, don't we? This is a stereocenter, and this is stereogenic center. So I took this one to look at the proton here in the NMR, and I won't show it to you, but that proton is a singularity too. And that kind of speaks the message that this thing is, it's homochiral in one chain. They're all R or they're all S. And then finally, I was just desperate. I said, well, take AZT, which I got a few hundred grams of long ago from a generous man in India who was giving it to Africans almost for the cost of making it. And AZT is a QACT reaction with this acetylene. That's 100%. There's no doubt about that. I mean, that kind of reaction is going to go really well, and it did. And then we got something, a nice white solid that we didn't make. We made the other one too, the adenosine one, to see if we could. But you see, this one is doomed to be mixture because it has a homochiral piece, and it has an R chain and an S chain. So at this point, the spectra don't look singularity anymore, but I think they're still helical on the one side. I don't know. We're going to find out more about that. Okay, now imagine that you have a three-step reaction. And here's the first step. And I've just cheated and cut off the other part that makes it a polymer. So now I just have this aniline difluorosulfur. And I take off one of the sides here. So this is an imaginary experiment, but you can bet it would be perfect because these single reactions like this are very reliable. So now I have this, and then I keep suffix catalyst again, and I put in the side chain, and then I do the AZT reaction. And so I guess what I'm trying to say is the yield here would not require, I mean, there would be no workups, and you'd be able to make kilos of this. If it was an anti-drug virus, antiviral, you can imagine that it could be. It looks like something that could be. It's about the right size. So this is just a way of explaining to you that normal synthesis always entails purification after each step usually. And so the reason for that is the reactions aren't perfect. And other technicalities come in, which this chemistry that we picked it to be limited but near perfect doesn't have. So now I go fishing with the aryl fluorosulfates. This is what we make. We make these from the phenol and the Vicane gas with the DBU and the other catalysts, BEMP. Oh, we got other catalysts too, like the ones that DuPont used to make chain transfer polymerization, like bifluoride catalysts of sulfonium ions. They're excellent. So we go in with what we have here is we put on the fluorosulfates in different ways. This is from ESF, but these fluorosulfates are almost totally. I mean, now we're talking sulfonyl fluoride. They're almost totally dead, and I'm going to tell you more about. They're more the ones that are aromatic are more reactive. But here now I have a fluorosulfate, not a sulfonyl fluoride. These are less reactive than sulfonyl fluorides, but they're also unreactive in water. I'll show you one thing right after I finish this set of slides that really is a lesson in what the weirdness of this chemistry is. And they just don't react with anything at neutral pH, even 200 degrees C. They're just not going to react. But it turns out that if you have an enzyme that's alive and naturally folded and doing its thing, they are not safe. The enzyme can make them react, and it can grab a tyrosine. these things can grab a tyrosine. And then that's a covalent bond, and that bond is forever stable. So this is like we call Sleeping Beauty, because if she finds her prince, she's not safe. She's going to be married to him forever. My wife's named that too. She named click chemistry as well. She's a writer, and probably also, she's a genius too, but we both had trouble concentrating, so we were kind of rather unusual struggle when we try to write together. Okay, here, this tyrosine I'd hidden before, because we did this with Jeff Kelly and Dave Mortensen and Wen-Tao Chen and Jia Zhedong, but these tyrosines are in a protein, I forget which protein it is, but you see what happens, this tyrosine here is now got this drug-like molecule. It came along and there was a fluoride here. And this fluoride was extruded by the environment here on this protein only if it's alive, and it made a covalent link. And now this enzyme is dead forever. It's not a bad thing. It's just that it makes the inactive site is defunct until the enzyme gets made over again. Oh, it's tyrosine 57, 229. This was with Kelly's lab, and we've got about 50 or 70 proteins that we can capture and identify and get about 10 X-rays. I'll stop here just for a moment to show this. This is, to me, amazing, because how many of us know that that's what's behind us? Always in a plane. That's the wingtip vortex. And that's what can really take you, if you're a small plane in a big wingtip vortex, it just turns you right over. Well, anyway, it's a kind of metaphor for what I see in chemistry. You know, what's happening and what we think is happening and what we hope is happening. You know, this is a fig Newton of our imagination a lot of times. And so I just like to remind myself that this is what we're trailing. And there's lots of beautiful pictures of wing turbulence. This is a DC-7 coming into O'Hare. It's coming down through a cloud deck. That was, and somebody was there with a camera. Probably in the air, too. Well, this is a joke, but there's a coach who had polio, a famous coach, Vince Lombardi in the United States, and he said, winning isn't everything, it's the only thing. And he was the greatest coach of the Green Bay Packers, and one of the greatest coaches of all time in football. So I adopted this. Reactivity isn't everything, it is the only thing. And structure does matter, but you've got to get the structures. And if you don't have reactivity that's the kind you can really rely on, you can't get very far. That's the problem. So that's all I have for that. I just want to show you one more thing that, if I can find it here. Yeah. This story of sulfex and sulfates, now that they can be made, and the fact that they don't react. You know, we're used to dimethyl sulfate as being lethal. I mean, if you breathe it in, it'll kill you. It's an alkylating agent. But it turns out that phenyl sulfates don't have any way to react. And even many sulfates like this don't react anywhere except the sulfur. And when they have a saturated oxygen on them, they're aliphatic. Wow, that kills that sulfur terrifically. Now remember, this would be a case where phosphorus here, weight drops to 31. This weight is 32 for these atoms, 31. And then because we're missing a nuclear proton on the phosphorus, we have a phosphate, POS2 minus. And that's something that looks even harder to hydrolyze, but that's what the enzymes can get a hold of. They bite it. They can't see the sulfate. I'll show you a thin layer in a minute. The sulfates these things are invisible, and they go through the blood-brain barrier and everything. They're a functionality without properties, sort of like that famous novel, The Man Without Qualities. They have no qualities. They have no properties. They're just whirling around. This one here is our favorite compound, right? As organic chemists, we remember growing up making tosolates, right? Everybody loves tosyl chloride. It's crap, though. It just goes to hell so fast that you have to get a new bottle all the time. It's very unstable, barely existing. This is really bad type of functionality. This guy is nearly immortal. And we had a bottle that was 60 years old when I last looked, because it came from a company that went out of business. And I got it from an MIT professor. We were young there, and our group got to raid his lab after he died, because the young people get to use the old guy's equipment first. And I got this bottle. And this compound is still absolutely pure as driven snow, and it's been across the United States in the summer, in August, 3 times. And it never got any kind of problem. That's how stable they are. And it was known back in 1927 by Steinkopf, Wilhelm Steinkopf and his group. They have wonderful papers in the Journal of Practical Chemistry. That's just amazingly cool. I think that's my ideal, the Journal of Practical Chemistry. And you can do it in a bathtub, you know, with a drain hole to get the product out. And that's why I need simple equipment, because I'm not too coordinated. And Sutter, this man was a genius. He was very smart. He taught beautiful aromatic chemistry and all about sulfur. That book I really treasure. That was published in '44, I think. And then, anyway, this was lost, but Sutter had seen it in '44. It didn't surface again, except 1 or 2 people noticed this paper. And what it teaches, of course, you have to read German, which is one of the things I learned in my Quaker school, because we had an exchange with Germany after the war. So I knew German really well, and it helped me. I read this years ago, and I tried to get students to reproduce this work, but they couldn't. And then comes Jaja recently, and let's see if I can... Well, it's just so stable, these sulfur fluoride. I have to go right to the fact here, so I won't take too much time. This is the most stunning reactivity phenomenon I ever saw. And the more I look at it now, the more I realize that it should have gotten more attention from me than it did. I was trying to make ligands with the sulfur chloride ones, and they were screwing up. So I said, we got to get the phosphorus, the sulfur fluorine bond there. And that's what did this. For most chemists, this is refluxing aniline. Well, this is what Steinkopf did this experiment. He took 40 mils of aniline, refluxed it, probably distilled it. It was, for us, we do it under nitrogen. It's water white. It's dry as a bone, of course, at that temperature. And then he put in this benzene sulfonyl fluoride and heated it for 3 hours and said nothing happened. Well, I just didn't believe it. So I went in the lab and we did this again. And sure enough, absolutely nothing happens to this. And I even bet we can take this to 240 degrees if we put a pressure tube in, and it won't react. That shows you the fluorine needs help. She won't come out without a lot of help. And that helped. Here's another one. This is crazy old German chemistry. You take dry copper powder. Fraser, you know about this chemistry, right? Ullmann chemistry. Dry copper powder, and you heat it to 230, 40 degrees, and you put a neat sulfonyl fluoride. This happens to be, you put a neat aromatic iodide, and it makes a coupling. Well, he did this for the ortho, meta, and para, and he got the products. Not perfect, but if you put the chloride in here, into that thing, that would be an explosion for sure, a redox explosion. That's my prediction. And here's the nice thing about these sulfates. You can make them, we make them from the silyl ether on either side and come in with the sulfonyl fluorosulfate, and you get this link. It's almost quantitative, fast, and you can have functional groups that look like they'd interfere with this chemistry. Certainly it would if the chloride was there. And so you get these links, and then all these are stable in stomach acid, in pH 1 or less. They're stable forever. I think stable in refluxing concentrated HCl, or even hot sulfuric acid concentrated. They're not what you think they are. And here's another way to know they're not what you think they are. And this we know, those of us who have organic experience know that if you take a phenyl sulfonyl chloride, like tosyl chloride, it'll be very nonpolar. This is 25% ethyl acetate hexane. standard non-polar solvent. Farnesol runs to about here. So it's a nice source. For terpenes, it's a good range. And here you see it's up here high. But the calibration for you is benzophenone. Benzophenone is here. And so these compounds are even less polar, a lot of them, than benzophenone. The sulfone is more polar. Sulfoxide would be more polar than this, of course. It would be down here. But look at all these compounds. They're showing their nature. This is very nonpolar, this diaryl sulfate. So that means that they're really not having any minus charge on their oxygens. And that's another conundrum because nobody talks about that in bonding. I think this whole bonding area is really messed up in sulfur and phosphorus. There's no pi bonds, but everybody writes pi bonds. And here we go with HPLC. This is HPLC that the least, this is C18 column in reverse phase. So that's the least polar compound. That's 4. So here it is. It's the least polar of the compounds. And we have lots of other ones. I shouldn't take too much. This was just to show you something pretty cool you can do, though. If you change a phosphorus, if you put this is diphosphate analog of the disulfate. And all I've done here is, if I could do it, it would be to add a nuclear proton, then I get the sulfate. That's because there's no other isotopes there, so it's an actual 31 to 32 weight change too. And I'll show you what it leads you to realize is that, well, first of all, you can't attack phosphorus chlorine bonds easily and reduce them. That's why you can make triaryl phosphates, but nobody was making these. And I have to quit now, so I'll just run ahead. I'm just saying there was tons of these phosphorus 5 triaryl phosphates and phosphines, but there were hardly any sulfates in the literature at the time we did this. So that's exaggeration. Nothing like that is ever true in chemistry of human judgments, but I say it essentially never happens. And there's a little beauty that makes Vicane. And I want to just get to the part where, yeah, well, Vicane, you can put it under pressure at 140 degrees and put sodium metal in, and it melts, and it just looks at the Vicane. Silver balls flurling around. Try that with sulfuryl chloride. Okay, that's it. Thank you so much for your invitation.
So, wait.
Oh.
So, I guess we have a time for a couple of questions. If somebody would have a question, please raise the hand. We have a mic here. So here we are. Please identify yourself. Yeah? Can you hear it?
It's very good. Back there. Oh, was it okay? Oh, thank you.
Okay, it's easier.
Oh,
Okay, so
yeah.
is this on? Yeah, so just a question. One of the molecules we'd want to make is to write the genetic code, so synthesizing DNA, now that we're so good at reading it. So do you see applications of click chemistry where you could approach 100% efficiency to create these long polymers?
That would be great if you could do it. It sort of occurred to me that they use phosphorus. They do triazole chemistry of catalysts. Is that you're talking about just making some way to make the diphosphate backbone with fluoride?
Yeah,
or,
because
yeah.
currently to make like a 200 mer, 300 mer with 99% efficiency, the full product is...
Did you do that?
No, but this is commonly done in the DNA synthesis industry.
I know, but then...
Getting beyond that, do you see any possibilities?
Well, I think you should do it, because I bet there's something in that. It's been used as it was given to us for so long, right? There's hardly been any engineering done on that thing. I mean, chemical engineering. Okay,
maybe one of your new companies will do it.
I don't have any companies. I couldn't take the company straight. I mean, I don't really... I have trouble. I don't really believe that information is good to keep away from people, although I did hide. I can't talk about our best stuff. We got really lucky again, this time in China, another perfect reaction. I didn't mention that. But keep your eyes peeled, and I'll send it to you guys who are friends as soon as I can. And John and I are writing it now. It's really amazing. But that's just by way of saying, you can't say that these perfect reactions are not there for us. I mean, the universe has stuff out there, and we got to get to it somehow. And we can't give up just because the governments don't give us money or whatever. We can do this kind of thing in your garage. It's not that hard, you know. Some of this chemistry really does. It's not. Sorry.
Okay. Any other questions?
Okay, thanks to you. You understand it? Yeah, sure, sure.
While you guys set up, I guess I'm going to introduce you. Okay. Can you hear me now? Okay, perfect. While it's okay. While Eda's setting up her talk, why don't I already introduce her? Although she probably doesn't need a lot of introduction. So I think it's fair to say that Ada is a legend in the field of structural biology, and not only has she provided breakthrough findings in how the ribosome translates the genetic information into the protein form to provide workhorses for the cell that catalyze most of the chemistry that goes on in all of our cells, but also in pretty much all of the cells on this planet. But in addition, she has helped numerous structural biologists, myself included, advance their studies in how proteins function, how their shapes dictate their function. And then on the practical level, this of course translates to widespread use of cryocrystallography in drug discovery, where it forms the basis for structure-guided drug design. And this is how most of the current therapeutics are developed. And I thought about saying a few words about Ada's background, but I think maybe it's not needed, just to say that the list of her awards is too long to list here. And she is currently chair at the Weizmann Institute, where she's been active many years. And from what I hear, she is very active today. So I'm excited to hear what she will present to us today. Ada, please.
Thank you. I usually don't do it, but now I will. You say that I'm the chair of the Weizmann Institute? No! Only a little center within it. Yeah, of the little center, but not of the. But it's immaterial. So you heard earlier in the previous lecture about bonds, and at the end even about DNA and translating the information. And this is what I will talk about. It's a big. No, the opposite. Less.
What about the camera?
A camera, I don't care. I care about good lecture.
It's all right.
Can you give even less? I don't need him. The camera is less important because they want to photograph me. They didn't even ask for permission. What's more important is that the lecture is seen by the people here, much more than what the camera sees. So please forgive me. I want as much dark as possible. Is it possible to get a little bit more dark? Okay, well, let's see how it goes. So I think that you all know that the central dogmas say that the genes, the DNA is the home of genes. The genes have the information what will be the sequence of the amino acids in proteins. I hope I don't have to explain it. I just want to tell you that maybe you want to share my excitement that all the DNA language is 4 letters. It was found when I was in high school. For you, this is, for young people here, this is a non-information, not important. But for me, it was, and I'm still now, until now, very excited by the fact that all, not only our life, but all life on Earth, and maybe also more than Earth, is dictated by 4 letters. So the 4 letters are here in the DNA. Each 3 of them is coding for an amino acid within all the proteins. It's correct for all. So in order that the information here will be accessible for whatever the cell needs, considering it, the first thing that happened is that the DNA is being transcribed to a similar molecule, RNA, in this particular case, messenger RNA, which is like DNA, but again, 4 letters, 3 of them exactly the same. The 4th is slightly different. But what is important is that the main chain of RNA is different from DNA. It doesn't have to be in a double helix. It can live as a single chain, and therefore the information is accessible and can be translated to proteins by ribosomes. Ribosomes are doing it in every living cell, from bacteria to the biggest animal, including fish, cockroaches, whatever you want to think about, flowers. And they work very fast in vivo, actually almost continuously, because the cell is making its proteins almost all the time. They can form up to 40 peptide bonds. Peptide bonds are the bonds that connect amino acids to each other. 40 in a second in bacteria, 5 to 10 in human. But anyway, very fast with a mistake rate that is hardly any mistake. About 1 to 500,000 to 1 to 1 million, depending how one define mistake, in which step, but it doesn't really matter. It's very little mistake. And I just want to tell you that me being a very fast student, I had to make a single bond. Took me 6 hours, 1 bond, the fastest in the class. And now chemistry, and I'm sure you know, chemistry developed and improved. So it's 1 to 2 hours in the lab, but not 40 in a second, and hardly any mistake. And there is a huge number of them in some human cells or some other eukaryotes. They can have 4 to 5 million, at least in some of them, namely in the liver. Even bacteria, when they grow, 80 to 100,000 in one. So now that we know how they are built, we think that we also know how they work. And we like to describe them as a factory that is made of 2 floors. On the top floor, the information is being read. It means the messenger RNA comes in. And in the lower floor, the bond is being made. So the amino acids are brought by trucks. If it's a factory, but actually it's transfer RNA, tRNA molecules. And when there is here the triplet that codes for that amino acid, it will come in and be connected to the growing protein that will go out from the lower floor. This arrow had to be inside the factory, but I don't know to draw inside, so please forgive me. The truck will come out empty. It needs a little energy. It's a rather efficient reaction, and once it's finished, the code will progress in 1 triplet. That's all. So simple. So just to remind you, you talked about making bonds. So these are the bonds that are being made between 2 amino acids. They are already connected to the tracks, which are tRNA. So I wrote it here in R if there is no water, and this is the peptide bond. And the biochemists have decided that in order to see whether ribosomes are active or not, they are using what they call fragment reaction. And these are tRNA 3' ends, the lower end, with two compounds. One is really an amino acid, and the other is similar to amino acid, so the reaction can stop here because this cannot be extended, and they know whether there is a bond. That's the way it's being checked since the 60s. So actually, the factory that you saw earlier had 2 floors, and the ribosomes are made of 2 different and independent subunits, a small and a large. This is correct for all ribosomes, from bacteria to the highest organism. The ribosomes grew, with evolution, grew a lot, from 2.5 million Daltons to 4 million Daltons, but the active sites did not change, and the reaction did not change. So the small subunit has the decoding center where the code is being read, and the large subunit has where the peptide bond is being made, and it's called PTC, peptidyl transferase center. And they are connected by this yellow thing, which is the tRNA, and of course by the complementarity of their surfaces. So once we saw the structure, we thought that we understand how ribosomes work after 20 years. And we made a little clip together with 2 students of the Art Academy in Jerusalem. Can you please put off the light so people will enjoy it more? I always have fights with the camera people. It's part of my existence. Okay, so I'm sorry, you'll see what you see. The students say that all the cells are green or should be green, so this is why we have a green background. And what you see here is the DNA reaching the small subunit and entering it to its own path, as you see here. And this is all monitored by factors, cellular factors. So in bacteria, there are only, only 3 of them, and this is initiation factor number 3. In higher organisms, many more, but the philosophy is the same. There are factors that tell the ribosome, now you have to start, and make sure that it starts and works correctly. So here they come in. The initiation factor is the blue thing on the right side. The rest is the small subunit. And you see it monitors it. And when it is happy, the next step happens. Another initiation factor, number 2, you see it down there in light blue, is carrying the first track, which is tRNA molecule, to the first position. And you surely know, I don't have to explain, that at least 2 tRNAs are needed for each bond making, the 2 components. So there are at least 2 sites. Actually, there are 3 sites, one for the exiting tRNA. So the center one, where the peptide bond is, the peptide chain is coming out from, is called P site, from the word PTC before, peptidyl transferase. And this is the first site to be occupied by the first tRNA on the small subunit in the decoding site. So now you can see the two factors are happy, they are living. And from the right side, the large subunit is reaching. It will not connect with the small subunit until the factors left, like that. And pay attention on the top side. Even bridges are being made, conformational changes. There are 13 of them, even in E. coli, in small bacteria. Now, this clip is available in YouTube. Also, the next one, for the last 15 years, I have lots of hits on it. I didn't put it in. I don't know who put it in, but doesn't matter, it's there. And nobody complained so far, which I think that may be correct, the way we see it. The sizes and so on are from crystallographic determination. So now we have the whole ribosome, the whole active ribosome, and we look at it from the solvent side. On top is the large subunit, below is the small. And you can see from the left factors, which are called elongation factors, bring in the tRNAs, and the ribosome helps. In, out. Look, 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 the two hands, in, out. Each hand is almost 100 nucleotides, 40 times a second. Unbelievable. And the bonds are being made in the lower side, but you can see now we took away the large subunit, so you see the decoding on top and the bonds lower, and the newly born protein goes into a tunnel. This is the red thing that protects it, and it actually spans the large subunit from top to bottom, so now we put back the large subunit, and you can see it's shining, and the protein in the lower part is coming out and folds correctly alone or with chaperones. We won't talk about it now. And the reaction continues until there is a stop codon, says the protein is made, and then factors like release factor and recycling factor, this gold thing from the left, is coming in and terminates. So the two subunits are now separated. The protein, the blue thing from the low, can go and do what it needs. And the rest, the tRNAs, the messenger and everything, is ready for the next job, the next protein. Usually they work one after the other, but this is what happens. Isn't it simple? Why didn't it take so long? So this is it. This is what the ribosome does. In the clips, you didn't see the exact structure. You just saw something that represents the size and so on, but actually we know the position of each and every atom. Now what you see rotating is a ribosomal, bacterial ribosome, but now there are many structures also of human or other organisms, and all types of problems too. But what you see rotating, you see that the ribosome is made mainly of ribosomal RNA. It's the small subunit that rotates. It sediments with 30S as its coefficient, 0.85 megadaltons, one RNA chain, 1,600 nucleotides, fairly conserved for each part of evolution, and 20 or 21 different proteins. It is where the genetic code is being read, and the large subunit is the same color code. It's much larger, 1.5 megadaltons, 3,000 nucleotides, and up to 34 different proteins. The number of proteins is less conserved than the rest. It is making the bond itself and protects the newly born protein, sediments as 50S. Actually, what you saw in the movie is two floors. The top one is the small subunit, the lower one is the large one. The tRNAs are reading the message here at the decoding center and making the proteins here in the PTC. And the connection is through tRNA, and I want a few words about tRNA. It's a molecule, it's a highly conserved molecule, but not fully conserved, that for all amino acids in all organisms, or at least in all organisms known to us, it's made of an L-shaped double helix with some changes here and here, but very conserved otherwise. All of them have an anti-codon loop and a CCA end, cysteine, cysteine, adenine end, where the amino acid is being bound to, and this part is the part that binds to the PTC. This is what goes into the active site. So when we look where the tRNA is bound to the ribosome, we look at the surface that accommodates it. The small subunit here and the large subunit here, we see that here, the decoding is being made, and here, where the peptide bond is being made, they are connected by the tRNA, but these two regions are just gray, just RNA, full RNA. It means the ribosome is an enzyme, which is a ribozyme, an RNA enzyme. And when we look into the active site, into the way this part is really built, we see that it's essentially providing a frame with a semi-symmetrical character because it has the same type, CCA amino acid, CCA amino acid or protein from the same sites, but it's only semi-symmetric. First, because all amino acids and tRNA have chirality, and second, because they're a little bit different. This side is taking the tRNA, and this side is, after the bond is being made, getting rid, so it's a bit different. Except for accommodating CCA amino acids, it's a bit different tasks. The ribosome here is shown in gray, and A site tRNA in A, in blue, and P in green, and I'll keep these numbers the whole way. So actually, the peptide bond is being made here. The newly bound protein can go out to the tunnel that I showed you, and this is fully conserved, this part. When we looked how the substrates are bound, and I show here substrate binding in our lab and also at Yale in another lab, we didn't work together, you see that they all occupies the active site in the same way, semi-symmetric, never mind if they are long here, or they are different substituent, but always more or less the same. And as I said earlier, the ribosome provides a frame, not a catalytic activity, just a frame with the stereochemistry that is suitable for peptide bond formation. So we looked at the sequence of all the RNA of the large subunit, which you can see here, the way the RNA is being drawn in 2 dimensions. We didn't see any symmetry. Any symmetry. We looked at the sequence, no symmetry. But when we looked at the structure, as you could see a second ago, there is semi-symmetry. And indeed, this is the region when we see the semi-symmetry, or almost symmetry, in here, only in 3 dimensions, and it's made of the 2 sides, the A and the P sides. The P where the tRNA in the P site is accommodated, and the A where the newly amino-acylated tRNA comes. This region is almost fully conserved throughout evolution. So what I show you now is the layout of this region in eubacteria, archaea, eukaryotes, mitochondria, with the A in blue and the P in green. You look only at the main chain. Can you decide who is what? After I drew it, I could not. They are the same, or almost fully the same. This is this part of the ribosome. When we look at it this is from top, from the side, we see that it has really a character of a pocket that can accommodate the 2 CCA amino acids in the A site and in the P site. From the point of view of conservation, the conservation of the nucleotides that make it, it's RNA, so it's all nucleotides, is very high. It's 100% for many of them, or if not 50 to 75% for all the nucleotides that make this pocket, and this is much higher than the rest of the ribosome, which is only 36 to 40% conserved. So the high conservation of the symmetrical region indicates that its existence is beyond environmental condition. And if so, if they are beyond environmental conditions, perhaps it represents a proto-ribosome, as it was before environment, before evolution. What does it mean? We call it a proto-ribosome, and what does it mean? A prebiotic bonding entity that was termed by us proto-ribosome is still functioning in the contemporary ribosomes, in all contemporary ribosomes, from bacteria to ourselves. Just to show it to you again, and you can appreciate the size. So this is the size, about 3 to 4% of the large subunit. It depends if we look at which one we look, but it always have this size, and tRNA here is a space filling, or the pocket, as you saw earlier. And if we want to look at it within the whole ribosome, it sits here between the large and the small subunit. This part is here, from top and from the side. So this is what we think how the proto-ribosome was starting, and it is also existing in the contemporary ribosomes. So based on the suggested existence of RNA-dominated world before life, prebiotic life, and on the finding that RNA can replicate and elongate itself and has catalytic capabilities, we propose that the proto-ribosome is not only the beginning of the ribosome, but it's the entity around which life has evolved. And this proposition I'll talk about in a minute. And the most important thing is that RNA can replicate and elongate itself and can bind itself to other compounds that were available at that time. So I don't want to go into long discussions about it, because it may be that we try to construct it in the lab. We spent 9 years trying to construct it in the lab. So we tried to base our construction of the current sequence and of RNA chemistry and RNA catalytic properties. I want to show you an example. For instance, in the proto-ribosome side, there is stem, elbow stem, which is a very common RNA feature, also in what is called ancient RNA. And one of our hypotheses suggests that the catalytic proto-ribosome is a product of dimerization of these two pieces, one like I showed earlier. So in order to not to fall into too many too many ideas that were not completely shown, we started with what is happening in the ribosome. So we talk about this part. This part has a P and an A component, like here, like you can see here. And we made them. We repeated it. You can see that here there are broken lines. We took it from this part of the ribosome. And here we could make changes with no worries, and we have what we call our own mutations. We also made RNA pieces that should fold like this, for instance, this one. For all, we require that these RNA pieces that we made according to the ribosome or not can fold, can dimerize, and can produce a pocket. So the first thing we try to find who dimerizes. And we find that not all sequences dimerize. Here, for instance, there are only these two dimerized, here these two. Not all of them dimerized. I won't go into detail, but this shows that we found some type of what we call prebiotic Darwinism. Darwinism. Only few. It's a Darwinism, it's a selection on the basis of molecules, not of organisms, like what Darwin wanted. But it doesn't matter, we won't talk about this either, we just talk about the proto-ribosome. It means a proto-ribosome with catalytic activity. And this took another 4 years, but we got it. So let's just remind you, we talk about tRNA, and this piece is the one that is sitting in the pocket. Or, as you saw earlier, this is the reaction. And the fragment reaction, as we checked it in the lab, is shown here with each and every atom. We got a bond. We got a bond last February, and since then another 5 bonds for similar or different constructs. And if you want some chemistry, the first pocket was 67 nucleotides on each side. The whole pocket is 90 in each side. We characterized the dipeptide by MALDI. We have positive and negative controls, and the time is less than 1 second, we know now. And now we have 5 more protoribosome products. So we are really very proud of prebiotic. So ongoing experiments yielded several constructs, as I told you, with binding capabilities. And our hypothesis, to remind you, is based on the existence of self-replicating RNA molecules with catalytic capabilities, and on the assumption that the genetic code followed its product. Because, of course, this little machine did not have any code to decide which one you want. In our opinion, those that were needed survived. So this is the far past. What is the near future? The near future discusses next generation species-specific, eco-friendly, novel antibiotics. So over 40% of the clinically useful antibiotics target protein biosynthesis. Very clever, mostly by paralyzing the ribosomes. The natural antibiotics are the weapons that bacteria from one type is using for interfering with cell life of different species. It's bacteria against bacteria. It's bacteria or microorganism fights. And the first question that we asked is, how do the tiny antibiotics paralyze the giant ribosome? We center on antibiotics to ribosomes. So bacterial ribosomes are of molecular weight of about 2.5 million, and antibiotics less than 1,000, more close to 500. And of course, we have to look at bacterial ribosomes because we don't want to kill the patient. So what do, the bacterial ribosomes, bacterial antibiotics? In order to be effective, they bind to functional sites. So I'm showing here some families of antibiotics. And I will talk about what is a family in a minute, but you can see that they all bind to functional sites, like on the small subunit to the decoding, on the large subunit for the bonding, or in the tunnel, and the hinging, the motions that you could see part in the movie. They can stop them by just fixing the piece that has to move. What are the families? When the antibiotics were found, and maybe you heard earlier in the beginning of the century, in the 20s, first penicillin, but then erythromycin. Erythromycin is the first on ribosomes. The companies jumped on it, and they made better ones, faster ones, less toxic ones, whatever. By changing, they took the core that was bacterial made and changed it in all types. I don't even go into details. Each has some type of different chemistry. But actually, they used natural compounds that once we look at them now, like the center here, the core, very clever chemistry. But anyway, once we understood how the ribosomes work, as a bonus, although I didn't really expect it, but for me, a real bonus, we understood how antibiotics work. Much more than I expected in the beginning of this research. And I want to show you 4 that are examples of interesting ones. So what you see here, the antibiotic is this yellow thing. It's called edein, and it disturbs messenger RNA going into its path. Look, look, look. Huh? You don't have to be big in order to disturb. You can make it being small. It was found in Poland. And I won't talk about it now, maybe later. The second one, tetracycline, is useful. The first one was not useful because it's too universal, but the second, this one, tetracycline, It occupies the position of the A site tRNA. That's it. No second tRNA, no bond. So these two were working on the small subunit. I will show you now two that works on the large subunit. The first one is erythromycin, also the first for ribosomes, and it sits in the tunnel. Only a very short protein can be made, about 7 to 8 amino acids, and that's it. Blocks the tunnel, not fully, but enough not to let most of the proteins go through. And the last one is the most clever chemically. It just goes into the bond, clindamycin. And the doctors told me, not only clever, it's also good medically. Look, it just sits in the bond. Isn't it clever? Yeah. So let's talk about some problems. All ribosomal antibiotics bind to ribosomal functional sites, which are highly conserved and mandatory for clinical use. Is the distinction between the bacteria and the human, the patient. And how does it happen? As I said earlier, the functional sites are highly conserved. They bind to functional sites, so there is some problem around it, and I want to show you one example. So you look here into the large subunit from top, the whole large subunit. Here is the entrance to the tunnel. The dark green are the nucleotides, and the light green are the amino acids of the ribosomal proteins. And in the tunnel sits erythromycin, this red thing. So we wanted to see how it sits, and actually all the family that came from it, that I mentioned earlier, the macrolides. So it sits here in the tunnel, here, the red thing. The tunnel would have been useful if there is no erythromycin. You see here a cut through the large subunit, vertical cut. So the directions are tunnel, and we look at here. And here what we see is tunnel walls that can become a pocket to all macrolides, all the amino acids, the antibiotics that came out of erythromycin. Erythromycin here is in red, and some of them are blocking much better, fantastically, very good, but all of them are blocking. Each color of here is a crystallographic result. It means not a computation on anything. And all interact with one of the tunnel components, which is adenine in position 2058 according to E. coli. So the interaction is like that. Here is erythromycin in red, and this is this nucleotide. And here the affinity is just perfect. Like a very clever person sat in the bacteria and made this antibiotic. Fantastic affinity. Very, very high. Now, ladies and gentlemen, please have a look at this point, and you will see the difference between bacteria and us. You think it's a big difference? No, it's only A to G. That's all. A to G. And when there is a G here, a guanine, this distance is too small. This van der Waals distance is too small, so there is no binding. That's the way, this is the selectivity of erythromycin and all the macrolides. A bigger problem, selectivity is a problem, but not as large as resistance, which is one of the most severe problems in modern medicine. So I'll talk about it in a minute, but I just want to show you one mechanism of bacteria to develop specific molecular pathways that cause resistance. It's not the most used, but it's the easiest for me to explain. So you remember selectivity was A to G. Here, these are bacteria, and here are higher organisms, even archaea. What's a big deal for bacteria to become G? That's all what it does, and now it's resistant. It needs a few enzymes for it, but it can do it. Actually, resistance is usually blamed on doctors. They are oversupplied, or the farmers that are using too much of it. but resistance itself started by bacteria against bacteria. One bacteria was throwing stones, like antibiotics, and the other didn't want it. So it developed mechanisms for resistance. And this was found by looking at the gut of a tribe that lives in Venezuela in the jungles, where they never saw any Western medicine. So what really happens in our mind? During bacterial cell division, acquiring genes from other bacteria or by itself, there are many mutations, and those mutations that lead to resistance are winning and staying. So there are so many of them, and it seems that we will soon revert back to the pre-antibiotic time, and people died from pneumonia or wounds. Or, as the World Health Association says, that we are coming to post-antibiotic era. And even the World Bank estimated about 4% of the global economy to be lost by resistance in 2050. Yet, very few new antibiotics are in development by the companies. Very few, hardly any. You want to see something? This is how resistance grew in 3 different bacteria, and this is the amount of new antibiotics. The last 20 years, less than 3. So my own opinion, can we combat resistance to antibiotics fully? I think it's unlikely, because bacteria want to live and because bacteria are cleverer than us in terms of survival. Yet, our little lab have some modest contributions, and I won't talk about everything. I already see that he wants me to finish. So we thought that, first of all, wide spectrum antibiotics are bringing more and more resistance, and we talked about specific ones. And the concept is, doesn't matter how the pathogenesis started, we will stop the ribosomes of that bacteria. So we determined the structures of ribosomes from pathogens. We did actually already 4. We learned that all bacteria ribosomes are similar, not exact, but similar, that it's possible to increase antibiotic effectivity. We are collaborating with Nabriva in Vienna, and they do it. Also, in principle, it's possible to increase selectivity. For instance, here, this is the site that accommodates erythromycin. In all bacteria that we know about, pathogenic or not, it's the same, so I drew it only once, but the protein that is next to it is different between pathogenic and non-pathogenic bacteria. In non-pathogenic, it goes all the way to here, but in pathogenic, it stops here. It means this is available for increasing the size of erythromycin, only for the pathogenic, but no company wants to do it so far. Also, beyond my expectation, we found novel antibiotic binding sites, which is, in my opinion, what we should do. For instance, here you see on top of a non-pathogenic in gray, the pathogenic insertions in bluish. Statistically, it didn't make much impression on the statistic. People said, less than 10%. But if you look at this less than 10%, each of them has a structure of its own. So essentially, if we look at it in more detail, the neighborhood is the same in both pathogenic and not. But this part has a structure of itself, unique structure, and it's available for, in our opinion, potential new binding sites, and we found 25 of them in a model system. We blocked one after the other chemically, and 16 of them, when they were blocked, inhibit protein biosynthesis. And since they are not involved in the primary ribosomal activity, no pathogen has so far, no pathogen has genes against them. So this means that, at least for now, we can think about design of advanced degradable antibiotics and environmental friendly. So I didn't talk about it, and I want just to mention. that the microbiome, it means the good bacteria in our body, which is located in guts, ears, lungs, and skin, they are all very, very useful for our life and our health. And all eubacteria, it means they all can be damaged by the currently used antibiotics if the antibiotics can get to these positions. What we think we should preserve them. So I'll say a sentence about it later, but I just want to talk about environmental and ecological considerations first. So most of the ribosomal antibiotics are extensions of cores that are not digestible. Not digestible, it means it goes out of us to the sewage or the waste, that you want to call it. But because they are so small, the purification systems not always catch them. So they can go back to the irrigation and come back to us by the grass that grow on it, or fruit or flowers, or, sorry, we don't eat flowers, but fruit or vegetables and so on. So we can, when we do ours, when we produce ours, we can build them as either degradable or at least made of materials that are not poisoning. And we can optimize their chemical properties, antibiotic action, and degradability. So far, we did them by nucleic acid or oligopeptides or similar. Very simple, with edges that can penetrate through the cells, through the membranes. So in summary, a new insight obtained from these high-resolution structures of ribosomes, from a genuine pathogen, now we have 4 of them, giving us tools for suggesting novel sites, for suggesting how to improve, for better distinction, and for making pathogen-specific antibiotics, like what people talk about medicine, personal antibiotics, when the persons are the bacteria. But this is what we are aiming doing now, and no company wants to collaborate on this with us so far. So in short, our structure-based species-specific antibiotics are designed for minimizing widespread resistance and microbiome destruction and environmental hazards. I'm sure that there will be resistance to them too, but maybe it gives us 20 or 30 years until, and meanwhile we can make more and more because we have many more sites. We can go cocktail by cocktail. So why did I connect the two subjects together? Because I think, you remember this addition? We see additions like this in several places. If we look at them closely, we see that the addition of eukaryotes from prokaryotes, the addition with evolution, is sometimes the same like the addition for the pathogen, for pathogenetic. So the question that I want to ask, and you can see here, this is the normal bacteria, the eukaryotes, and the pathogens. The question that I'm going to leave with you is, are pathogens the missing link between eubacteria and higher organisms? I don't know. So at this point I will stop. I will thank the Weizmann Institute that let me work on what was my dream for years and years. I want to thank the Max Planck, especially Dr. Wittmann, who let me collaborate with them, and then was important and started a little research institute for my group in Hamburg, where we collected the crystallographic data. He really wanted to see the structure of ribosomes, but he died 10 years earlier, was replaced first by Franceschi and then by Fucini. So I had 2 groups at the same time. I don't want to go into details, just to thank them. And I want to show you, especially the young ones, the group in Israel. It's actually not everybody is working with us now. Some have finished the last 5 to 10 years. I want to tell the young students here that I'm not the person that runs the lab. Dr. Anat Bashan, a fantastic scientist and fantastic mother, is doing it, so it's possible to be scientist and mother. She has 3 children. Ella has only 2. I don't want to go one by one. Raz has also 3 children, but he is a man. Let's talk only about girls. So let's talk about Tamar. Tamar came 16 years ago for 10 weeks. She's still around. The day that I took the picture, she had birthday, and she baked the cake. Can you see the cake? I'll show it to you in detail. Huh? And this says that in my group, ribosomes are considered sweet. I want to thank my family. I show here only my daughter, who is an MD, and my granddaughter, who, when I got a prize in Paris, made a speech about me. And she said, as you know, it means me, is a very busy scientist, but she always finds time for me, and therefore I invited her when I was 5 years old to the kindergarten. She gave me a prize. Not this one, this is the Nobel medal. But for me, her prize is at least as important. The grandma of the year is Ada Yonat. So when I asked her which year, I said, which year you have to reprove yourself every year. If you fail, I take it off the wall, and you can see it's still on the wall for the last 11 years. Ribosomes became popular in Israel. He's me, and his wife, you see here, she's the ribosome, comes out. Also, young children became ribosomes. And Kishka, who is a fantastic artist and writer, he made ribosomes as head full of it. But if you look at it carefully, there is a symmetry here, twofold symmetry. Small subunit, large subunit, large, small, and small. He's not a crystallographer, he's not a scientist. He did it on his own from the web. And he thinks that new antibiotics should be here, 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 and there. Thank you.
Thank you very much, Ada. I think we have time for 1 or 2 questions. Anyone? Over there, there's a question.
Yes, I'm Georgi Popov from University of Helsinki. You said that no companies want to collaborate with you on this research. Can you comment why?
I saved it for you, but they explained me. The investment in developing an antibiotic is very high and very expensive for them, takes a long time, and at the end, usually antibiotics are used for a short time, 3 or 4 weeks. It's not like the cocktails that they give to elderly people with 5 or 6 or 7 pills for diabetics or blood pressure and so on, that they sell all the time. So this is the profit. It's not like the compounds, the therapeutics that they give to cancer or to Alzheimer, that everybody will pay everything. So it's the difference between the profit and the amount of investment disturbs them. And I understand this. They are companies. They have to make money. But when many will die young, at least they will lose their elderly people and many of the cancer and Alzheimer and so on. So maybe they will have to collaborate on this. And when I tell them to them, they really hate me. They don't want to hear it.
Just fabulous talk. I'm just sitting here. How do you get all these resistance informations into the jungle? Is it coming through the oceans with all the viruses and how are they, the horizontal transfer, how do they get this information when they don't have this?
Horizontal transfer, maybe the ocean, but maybe also a little mud or a little river or whatever.
Something is traveling, but the biological information has to get to them somehow.
Yeah, it happens. Yeah. And I'm not good at it. I cannot tell you. It may even happen in the stomach of animals or people.
Bad news, though.
But mutations happen all the time, naturally, without any.
So why do we even try?
Because we want you to stay alive with us.
Well, that was actually my question.
Not only you, we want her to stay.
Okay.
So it could be in the jungle that because a lot of these macrolides are derived from nature, that there might be a substantial concentration of those in the soil where these bacteria that these people digest when they eat their food, wherever it comes from. So it might be that these bacteria have already experienced this practically the same antibiotics that we use to treat. So I think your idea to develop designer antibiotics is probably the way to go.
The fact that they survive show that maybe they are already mutated. And we can't look at all mutations. We can, but we are not doing it. We look only at the mutations that have something to do with antibiotics.
Okay, with that, I think we'll have to stop in the interest of time. So would you please join me in thanking Ada once more?
There is coffee served on a corridor. I don't know exactly where, but if you go out the door, you probably see it. I'm trying to look what time it is, so let's try to get back 5:10. I know it's really small break. 4. No, can't even read anymore. And I want to remind at this point also that after this seminar we have the get-together party there in the plaza where we're going to serve some bubbly drinks and something. We're going to give some prizes and so on. So please join there after this seminar. Thank you. How do you feel? Okay, great. Oh yeah, they do. The problem that once in a while they work too well and they feel like.
I like this drug discovery aspect.